Hello everyone and welcome to TamTech Academy YouTube e-learning series. In today's video, we are going to talk about control valve sizing and with a special focus on subcritical and critical flow. This topic is in general extremely important for process engineers, chemical engineers, and also who is working with the fluid systems because incorrect valve sizing can lead to noise, erosion, instability, and sometimes even equipment damage. By the end of this video, so you'll clearly understand the control valve sizing, how the flow characteristics work, the difference between the subcritical and critical choke flow, and the last one is how sizing equations are applied in practice. This is the final example. Let's start with basics and let's remember what we had learned in the previous class. In the previous class, we learned about what is a control valve. We said that control valve has a flow characteristic and it describes the relationship between the flow rate and the valve travel. It had the three different flow characteristic curves, which are the linear, equal percentage, and quick opening. Very shortly, the linear was flow increases proportional with valve opening. For the equal percentage, we said that each equal increment of valve travel produced the same percentage change in flow. And the last one was the quick opening, where we needed the large flow change at small openings in a very rapid, in a very quick manner. Usually we said that it's used for on-off services. And we said that it's very important to choose the correct flow characteristics because it's just as important as the sizing the valve correctly. Now we'll move to the control valve sizing. I believe that this equation is quite similar to some of you, which is the Q is equal to CV delta P over SG or just G in the square. So actually we said that this is a basic liquid sizing equation, and I have added the reference for your further studying purposes. So in the control valve sizing equation, we need four different actual variables. The first one is the CV, which is the valve sizing coefficient. This valve sizing coefficient is taken from the valve manufacturing datasheet, or like it could be also available on the websites on the internet, because most of the models, when you just type it on the Google, so you can easily find mainly the catalog. The second is the delta P, which you should know that the valve inlet and outlet the pressure, and with this one, inlet minus outlet, you can find the delta P. The G, or sometimes this is called like the SG, which is the specific gravity. So this is given for the specific gravity of fluid. I believe you can easily find it and you know how to find the specific gravity. So for example, if I write there, so my condensate, it's around, let's say, the 650 kilogram per meter cube. It means that its specific gravity is around 0.65. So you put the 0.65 instead of this G, and you can easily calculate. The last one is the Q flow rate. You can see here that so this could be interchangeably possible, this both of these equations, because sometimes you need to find this Q, sometimes you need to find this just CV. So that's why they are interchangeable, and you can find whatever you need from these equations. This is actually where the starting point for the control valve sizing equations for the liquid services. But you need to be able to, first of all, find out, so what is the flow regime of your liquid, of your fluid. To determine the answer of this question, we need to look for our answers in this slide. Generally, there are two types of the flow regimes to determine it, like which kind of equation we need to use. This is subcritical or critical flow types. So it could be a bit complex from the first side, but it's really simple. If your delta P is less than FL square to delta PS, so it says that the flow is subcritical, but the vice versa case, it's the critical. Normally, what is the FL? Your FL is the liquid pressure recovery factor. You need to be very careful with this PVC. The pressure VC means that this VC, vena contracta. So the vena contracta of the valve, the main value, the pressure, you need to put in the equation to find what is your FL. So in this way, you can easily calculate it's subcritical or critical. However, we know there are some simulations easily providing this FL factors and also values, and that's why it's easier to determine so whether the flow type is subcritical or critical. Many sizing mistakes in general happen because engineers assume that the subcritical flow, but in reality, the valve is already choked condition. So the other name for the critical is actually the choked. That's why I determine after determining the flow types, now we'll dive into that. So what is subcritical, what is critical flow? I'll start with the critical one. In general, critical flow it is the case that your fluid velocity at vena contracta reach sonic velocity. So if I show you the simple valve, let's imagine that this is your piping. So you have the valve. It's a very simple control valve. Where it's throttling, where it's controlled, it's part where is the vena contracta called P VC. So pressure at vena contracta determines your type of the flow. It's either critical, it's in the other case, it's the subcritical. So the critical flow happens when your fluid velocity at vena contracta reaches the sonic velocity or sound velocity, which we know it's like the highest one. So at this point, further decreasing downstream pressure, so it doesn't increase any flow, and it means that the valve becomes in choked position. It's in critical position. So after this point, there is nothing possible, and it is not even existing. This is very common for, in general, gases, steam, or physically what happens is like gas accelerates through the valve restriction here at vena contracta, and velocity reaches the speed of sound, and pressure disturbances it cannot travel upstream anymore. So as a result, your flow is controlled only by upstream conditions, not the downstream conditions. Okay. So for example, it's already upstream conditions. It is controlled here, not the downstream conditions. In general, the critical flow can cause the high noise, general the more erosion and severe valve damage, and that's why we can determine that. So our flow, it's already changed from subcritical to critical flow. It's already in choke position, and we need to do something on the flow. So we need to do some controlling ways in order to change this phase, because this is undesirable case for the valve actually, because at the end of the day, it will damage your valve and you need to change it. If we see the general critical flow equations, we have two options, which is the SI unit and the USC unit, which is the US customary units actually. So two types of the equations like available, but it's the same equation. In this case, so you shouldn't be like afraid of the equations, but CV or QV, whatever we want to find. So this general the CV, as you can see, you have again the QV, you have the FL, pressure recovery liquid factor, and P1 the inlet, and etc. But you have also DTZ and also Y, and these values are actually making more clearer, or let's say them more definite values it will give to you. That's why, so this is the main principle, or let's say the simulation background equations. So for the US customary units, you have these equations you can use. So it's actually inherited from the basic liquid sizing equation that I showed you before, which is this equation. So, and after this one, they have added some characteristics in order to make it more definite for the SI units, for the US units as well. Now we'll see what is the subcritical flow. In the subcritical flow, it's vice versa. The fluid velocity at the valve vena contracta is below the sonic velocity. If I show you that the same, let's say the figure now, which was again the control valve, we said that at this point, PVC, oh sorry for my P, okay, PVC, which is the vena contracta, already at this case, your fluid velocity is below the sonic velocity, which we want to have it actually in our valves. So which is the typical one. If it's below sonic, or let's say the sound velocity, it is in good condition. It means your flow rate, it still depends on your downstream pressure at this side. Okay, if you remember in the critical flow or choke flow, it was the vice versa. So we said that it only depends on the upstream conditions, not anymore the downstream conditions. But what happens physically? So we said that your velocity increases, fluid doesn't reach the sonic speed, and you can further reduce your downstream pressure as well, and flow will continue to increase. In general, the main characteristics is here. It's the normal behavior. It's the flow can be controlled. You don't have any choking or critical flow conditions, and this is very common during normal operations. So for the liquids, we'll say that no cavitation happens, and pressure at vena contracta stays above the vapor pressure. Why I made it red? Because most of the students know that cavitation only occurs at the pumps, but it's not true. It could also occur in the valves, which will result in the huge damage and also the erosion problems. In order to stay away from the cavitation, so I made it red. So you should be above the vapor pressure of the liquid. So that's why we need to keep it as subcritical flow, not the choke or critical flow conditions. So the key takeaway for the critical flow valve critical flow conditions, sorry. So never use any subcritical equations when flow is choked or your valve size will be completely wrong. For the subcritical flow, you should be very careful with this, the additional like the parameters like the D, you can see it here. It's very similar to the equation that we learned before, which was the QV is equal to CV delta P over SG. It's very similar. It's again the SI unit and US customer units. You can use whatever unit. In general, the KV and the CV, they have also the relationship between each other. That's why you should be very careful when you are using any of them. So, as an engineer, finally, your main responsibility is to identify first of all your flow regime, then select the correct equation, either it's subcritical this ones or critical this ones. The next one is the applying the manufacturer standards, because every manufacturer have different standards, have different, let's say, the guidelines. You should be aligned with them, and skipping any step could lead to the major design errors, and later it will have a huge problem in the operations. That's why you should be very careful with that. I have added one final quiz here, which is taken from the Emerson catalog. So it's the class 300 globe valve with a linear cage and NPS 4 Fisher ED valve at 100% travel. I have added the XT travel time and also the CV. So you can use this data. You can determine first of all what is the flow regime of the valve, and later is a subcritical this ones or is a critical this ones. You can easily size it. But for start, you can also try a very simple control valve sizing equation, but be careful with that. So the liquid sizing equation is completely different from the gas sizing equation. Thank you very much again. That's all for today's lesson, and thank you very much for watching this video from our TamTech Academy YouTube e-learning series. So if you have any questions, suggestions, or topics you'd like me to cover next, just feel free to contact us via our these three channels: Instagram, WhatsApp, Gmail, and etc. Thank you very much. Have a nice day.